Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits, and in this lecture we will be continuing our discussion on adders and subtractors. If you recall, in the previous lecture we started with binary addition. We spoke about addition for two numbers, then we spoke about half adders, full adders. We created a circuit for half adder and then we realized a full adder using two half adders. Then we spoke about 4-bit adders and we spoke about the problem of if we not having 4-bit adders, right? If we don't have, like, we have two numbers which are 4-bit wide, and if we directly go by k-map minimization method, it would be very cumbersome because we will have 512 truth table entries to look at. So basically what we did was we made a 4-bit adder using a 3 bit adder, which is like a full adders, and we used 4 full adders for that. And then we said, like, we said, like, in case we have to further add 8-bit numbers, what we can use is we can use two 4-bit adders, right? And the problem and the basically the thing is, right, as and when the number of bits increase, let's assume tomorrow we have like a 64-bit bus. If at all we don't use this lower level of abstraction, and if we don't use this half address or full address, or we don't create a circuit from top to bottom, the problem statement would be we would have too many combinations to verify. Let's assume we have a 64-bit adder, right? How many number of input combinations are possible? 2 raised to power 64. And if we have to verify the adder for all 2 raised to power 64 combination, it would be a very unbounded problem statement, because we would not be able to run so many of simulation cycles to be able to verify it, right? So in other words, right, for half adder and full adders are important ones, and they underlie the basis of formation of a bigger adder circuits. And we saw an example using a 4-bit adder. Now let's talk about something called as a 4-bit subtractor, right? So this is a circuit which we drew last time, correct? We had like 4 full adders for doing a 4-bit number addition. Now let's do one thing, like, let's talk about the next term. Let's assume we have something like, till now what we did was we did a plus b. Now let's assume we have to do a minus b. For doing a minus b, right, what we will have to do is we will have to take a complement of the number which we have to subtract. So basically a minus b is equal to a plus 2 complement of b, where 2c is equal to, it represent 2's complement, right? Now if a plus it's, and what is 2's complement is nothing but each term of the b, right? Each term of the b inverted, which is like 1's complement of b plus 1, right? 1c is nothing but 1's complement. This is the diminished radix complement. And what is 1's complement of b? It's b bar plus 1, right? So basically if my a plus b is same something as a plus b, my a minus b is nothing but a plus b bar plus 1. Now since our subtraction is a plus b bar plus 1, right, and we already had a circuit which we spoke about in the last lecture, which was something like this. Can I obtain a subtractor using an adder circuit, right? So basically, can I put a logic somewhere so that my b is converted into b XOR plus 1, right? So basically, as we spoke about XOR gates, right? XOR gate would come to our rescue over here, right? So basically, we said like XOR gates are like odd functions. One of the other uses of XOR function is they can act as programmable inverters. So basically, we spoke about it last time. So basically, what we can do is, if we say that if a number is XORed with 0, it's the number itself, right? If a number is XORed with 1, this is B complement. What we can do is we can create an XOR operator. We can XOR B with B to obtain B bar, right? XOR B with 1 to obtain B bar, and once we have obtained B bar, we can add to a circuit. So basically, let's assume that we have two input 4-bit number A3, A2, A1, A0. Then we have a 4-bit second number as an input, and then we have something like C, correct? When we had to output a sum results, we did S0, S1, S2, S3. and C out. Now if I have to subtract these two numbers, right, there's a mistake over here. I can put B0 and B1 and B0. Now if we have to subtract two numbers, right, how did we realize this particular circuit? We said like let's put four full adders back to back. This will give me S0, this will give me S1, this will give me S2, this will give me S3. I can simply put input over here as right B3 A3, B2 A2, B1 A1, B0 A0. We have a carry in, then we have intermediates carry and connected to carry, and this is the carry out, right? Now we said A minus B is nothing but A plus B bar plus 1. So basically, right, let's assume we have this circuit, and let's assume that we have to do a 4-bit add with C in as 0. So basically what we can do is we can tie in this for a 4-bit adder with 0 C in, right? 4-bit adder, we can simply say C in is 0, right? And let the numbers be like this. So this is like a adder. Now if I have to add a 4-bit subtractor, right, what I have to do is I have to add this extra 1. So what I can do is I can make my C in as 1. So if I convert this C into 1, my problem of number A being present over here is solved. My problem of adding 1 to the circuit is solved. But how do I convert B into B bar? And as we spoke in the previous file, right? B bar is nothing, but this could be replaced at B plus B XORed with 1. So basically, if this B, right, if I XOR this B with 1, which is like simple as saying that okay, we have this number B3 and we XOR it with 1. So this is B3, we XOR it with 1, this is B3 bar. So basically what we can do is we can convert, similarly we can do it for all the operators, like for example we have B0, we pass B0 through XOR gate, this will become B0 bar. Similarly B1, we pass it through X0 gate, this will become B1 bar when we XOR it with 1. Similarly for B2, B3, right? And what we can do is we can add 4 XOR gates, right? And what we can do is we have this extra input now, which is what we can say, this extra input which is 1 is something which we can call as Cin. So basically what we can do is we can connect this particular Cin to this particular portion, and for adder where Cin is 0, B XOR with 0 is B itself, and for a subtractor, like this is a adder where we will, and for a subtractor when we have B XOR with 1 is equal to B complement. So basically what we can do is we can XOR with Cin, and we can convert a adder to a subtractor easily by using a 4 XOR gates. So, and this can act like, so in this case carry line act like a select line where we can say if it is 0, my input to XOR gate will be 0, and the same circuit could be used as adder or subtractor depending upon what is the value of Cin. If my Cin is 0, it will act like a adder circuit. If Cin is 1, my input is 1, my each of the B operators will be like B complement, and basically I would be achieving this particular functionality. So this will become a subtractor. So this is one of the subtractor circuits which I wanted to talk to you about in this particular lecture. And what we saw was a simple circuit which was an adder circuit. We added 4 XOR gates, and this particular circuit could behave as adder or subtractor depending upon the value of Cin. Being 0 it's adder, being 1 it's subtractor, right? So once we have looked at this, right, now I wanted to talk to you about one of the problems we have over here, right? If you look at the circuit over here, which we drew, basically this particular circuit, what is happening over here is we are having 4 full adders which are back to back, and each of the full adder is made up of certain set of gates. Okay, to explain the problem over here, right? So let's assume that we have 2 full adders, right? One of the full adders I'm drawing over here, and the second full adder I'm drawing over here, right? Let's assume we have B1, we have A1, we have B0, we have A0, this is S0, this is S1, this is carry out, this is carry, and this is carry in. Now how this circuit looks like, right? So intrinsically this circuit is something like we have an XOR gate over here. This is A, and then this is a input A, this is a input B also. We have a B input, we have a A input. Then similarly both A and B are ANDed together as well. I'm just creating a circuit of a full adder, right? And once we do this, right, what we have is intrinsically we will have one more XOR gate where this is C in, and then we have this particular C in which is coming in, we will be ending it. This particular C in is ended with this XOR Y, correct? Basically this is becoming a bit messy, and what we do is this output is then odd to give us our carry out. This is our sum out, correct? So what is happening over here is this is nothing but a full adder circuit which we saw in the previous files over here, and if I have to pull that full circuit itself out, this is this circuit where our input X Y had to go through one gate, right? This is gate number 1 where we have XOR Y. Then we had a second gate over here which was the AND gate where we generated X and Y. And then both of them, right, we had a next set of OR gate where we had X and Y, XOR C in which we got, and then eventually we had something like this third gate over here. So eventually what is happening over here, right, my particular cout function, if you see over here, which I'm trying to highlight over here, so basically A, B, A is or B, so this is A is or B is or C in, this is A is or B into C in, and then basically this is an OR operation. So basically for propagating this carry out, right, what we are trying to do is we are passing through one gate. This is gate number 1, this is gate number 2, this is gate number 3. So basically my cout will be calculated only when I pass through these gates. So this example, whatever we have been discussing till now is called a ripple carry adder. So the diagram which we had discussed till now is a ripple carry adder because the inputs A0, B0, right, and C1, C in input, right, they ripple leftwards until my count Cout and S3 are produced. And the disadvantage of this ripple carry adder is they are very slow. And if you see, like, there's a long path, so I got A0, B0, I got C0. For to produce my final sum, which is S3, and my final carry out, which is Cout, I have to go through a long path. And in general, right, for n bit adder, the longest path would be 2n plus 1 gates. We already saw that for 1 bit there are like 3 gates, so 2 into 1 plus 3. For 2 bits we will have 2 more gates, which will, these gates would be replicated 4 and 5 again. So we, for n bit adders, we have a 2n plus 1 gates, and that would basically it would mean that for a 64 bit adder we would have a gate delay of 129 gates. So this is pretty slow method of implementing whatever 4-bit adder we did, right? However, there is a faster way to do this computation, and for implementing that circuit we have something called as a carry look ahead generator. And in carry look ahead generator, right, what we try to do is we try to create two terms. If you see, right, what in a full adder we had sum is equal to A XOR B XOR C in, and carry out is A XOR B into C in plus AB. This is my full adder operation which we saw till now, right? What we can do in a carry ripple generator is we will generate two functions. One is a generate function, one is a propagate function. For any stage I, generate function is nothing but AI into BI. Propagate function is nothing but AI XOR with BI. What we have done is we have eliminated the dependency of internal carries. What we have done is my G0 would be A0 B0, my G1 would be A1 B1. Similarly, my P0 would be A0s or B0. P1 would be A1s or B1. And all these numbers, right? These are my inputs. These I would know at the time input arrives. Correct? So, and what is the final carry out for me? The final carry out for me at the output, right? Finally, or intermediate or the final carry adder would be what? It would be Pi into Ci plus Gi. Correct? This would mean what? This would mean my C1 is equal to P0 Ci C0 plus G0, and which is nothing but I already know what is my C0, which is input. I know my G0 and I know my P0. Similarly, C2 is nothing but P1 into C1 plus G1, which is nothing but G1 plus P1 into C1 is what? P1 into C1 is nothing but this particular equation, P0 C0 G0. And each product term is nothing but it depends upon the individual inputs. Correct? In this way, what I can do is I can create all the terms. C3 would be something like, in this particular case, C3 would be G2 plus P2 C2. This is equal to generate 2 plus P2, and C2 would be something like, which we have already calculated, which will be G1 plus P1 G0 plus P1 P0 C0, right? And if we try to solve this, this will be G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. And if you see this equation, everything is in form of C0, which is like input for a user, and Pi and Gi. And Pi and Gi are both dependent upon Ai and Bi. So basically we can develop, or we can calculate my final sums and intermediate sums in one go. And these expressions are all sum of products. So we can use them to make a circuit with only two level of details, right? So basically my C0 can only be implemented by only two set of delays. So basically this is like one OR gate, which will ORing all the things. And these are like AND gates. And all these AND gates could be one level of like one level of delay. So this is something which is called as a carry look ahead generator, and this is important just for the this is important because we should know that there is a set of delays in the ripple carry address which we have seen till now, and this particular carry look ahead generator helps us eliminate that problem once we do our intermediate calculations. Hope you enjoyed this lecture. Stay tuned for more. Thank you.